Hello everyone, welcome back to the F equals MA Club. This is going to be the online recording for the day 6 lecture, which will be about rotational inertia and angular momentum. And sadly, since we did not actually have the club meeting, this will be the official recording, and I will strongly recommend everyone to fully watch this. Alright, and just another little thing, I'm very sorry for delaying this for so long. Winter break was pretty busy for me, but I'm back and I'm going to try and get this recording in as soon as possible. Alright, without further ado, let's start. So just a little bit of review. Last time we talked about circular motion and rotation. So for circular motion, we talked about translational and rotational analogs, where we had equations that were almost completely mirrored with rotational units. We had total acceleration, which was a combination of tangential acceleration and radial acceleration. If you want to learn more about that, you can go check out the previous video. For rotation, we talked about torque and force. We did a little bit of work on moment of inertia, and we tackled translation and rotation and how to deal with them in the competition. All right, let's first talk about rotational inertia, right? So last time we talked a little bit about this, and the big thing is that the rotational analog for our very classic second law, which is F equals ma, translates to our torque is equal to our moment of inertia times our angular acceleration. And remember that torque is applied for rotation. So moment of inertia, its exact definition is how much an object resists angular acceleration, which basically means how hard it is to make an object spin, right? And the higher the number, or the larger the number, the harder it is for an object to spin. Maybe you have a very light pencil, and if you spin it from its center, it's really easy. But if you have something like a ring, and a very big ring that was very massive, it would be a lot harder to rotate. And so there's many formulas for different objects. I would strongly recommend everyone to at least get most of these memorized, so the competition won't be too hard, because moment of inertia is a very big topic, and though previous competitions from earlier years did provide some of the equations, in recent years we haven't seen much of that, so it's just really good to memorize most of these equations. Alright, so the two rotational inertia theorems that all of you probably should know are parallel axis theorem and perpendicular axis theorem. Perpendicular axis theorem isn't really tested, but it is just something really good. Parallel axis theorem, on the other hand, is very important. So for parallel axis theorem, we see that our moment of inertia is going to be equal to the moment of inertia of our center of mass plus the distance from the center of mass to whatever axis the actual object is rotating on, squared times our mass, right? And so the reason why we say this is because the rotational inertia, or at least the moment of inertia at the center of mass, it's going to be the smallest moment of inertia for an object. And remember that this is only correct when we take this when it's from the center of mass. If we take another measurement and try and find the parallel axis theorem, it's not going to work like this. Perpendicular axis theorem, basically it's just like all three axes pass through the same point, and this is typically used for things like rectangles or triangles, and I can show you at this moment. It's going to be something like this, where we have maybe a plane or something like that, and we want to find and given like maybe the moment of inertia of the plane rotating around this axis and this axis, they may want you to find the moment of inertia rotating about this axis, or something like that. And so parallel axis theorem, on the other hand, let's say we're given a cylinder or something like this, right? Given a cylinder, and if you want a more detailed explanation, I would strongly recommend you search this up and learn on your own, since this is a very simplified explanation, right? So given a center of mass, given the moment of inertia of your center of mass, which I'm pretty sure is going to be 1 over 2 mr squared or something, given your moment of inertia from your center of mass, if we were to say try and find the find the moment of inertia of the cylinder rotating around this axis, then we would need to use parallel axis theorem, which, as written before, is like this, and we would get that our moment of inertia would be 1 over 2 mr squared plus this distance is going to be our radius, right? So we're going to get mr squared, and so that means that it's going to be 3 over 2. And one of the more commonly known ones is going to be a rod, a very thin rod, rotating about an axis, right? So if it's rotating from the center, I'm pretty sure it's going to be, let me just double check, I'm pretty sure it's 1 over 12, right? Yeah, so rotated about the center is going to be 1 over 12 times our mass times the length of the rod squared, right? And so if we were to find the moment of inertia around one of the ends, then we can take our moment of inertia from the center of mass, which is 1 over 12 ml squared, right? We can put the equation back here, plus the distance squared times m, right? So it's going to be m times, what is that distance? 1 over 2l, right? So that's going to be m times 1 over 2l squared, which is going to give us 1 over 12 ml squared plus 1 over 4 ml squared, and this is going to give us 1 over 3 ml squared if we rotate around this axis, right? And so that's the basics of parallel axis theorem and perpendicular axis theorem. It's just, I would strongly recommend that you memorize parallel axis theorem, since it will be very much used throughout the test. All right, moving on, we're going to be talking about angular momentum now, right? So the first thing is the conservation of angular momentum, right? So the typical example is like a ballerina. When they pull their arms in, they spin at a faster rate, and if you've ever seen a demonstration by a physics teacher or any other person, it's probably around a spinning chair, and once they pull their arms in, they're able to spin slightly faster. And so angular momentum, the big thing is that it's the rotation, so it's going to be the rotational analog of linear momentum. So we have our typical P is equal to mv. For angular momentum, it's going to be L, which is angular momentum. L is going to be equal to, L is going to be equal to our moment of inertia times our angular speed. And we can also say, for more high level, it's our linear momentum cross, and the cross product of the linear momentum and the radius, right? You can also say P times R in some cases. This is also something big. Basically, by using the rotational analog of impulse, we can say that if our torque is equal to 0, then our change in angular momentum also equals 0. And this is going to be a rotational analog of impulse, as stated before, where our change of momentum will be 0 if our force is equal to 0, right? Or net force. And so this is the big equation for conservation of angular momentum. We have that our moment of inertia times our moment of inertia, or at least initial, times our initial angular speed is going to be equal to the final ones as well. So that's the reason why a ballerina may spin faster. It's because once they pull their arms in, their moment of inertia will be much smaller and their angular speed will be greater, right? And so kinetic energy, there's two types of kinetic energy that we're going to be talking about. There's translational and rotational, right? Translational is 1 over 2 mv squared, and rotational, again, is going to be the rotational analog, which is going to be 1 over 2 times our moment of inertia times our angular speed squared. And remember that rotational is going to be for a fixed axis. So our total kinetic energy is going to be as shown here, which is 1 over 2 mv squared plus 1 over 2 I omega squared, right? And there's one more thing, which is rolling without sliding or slipping. There's two types of rolling. One is with sliding or slipping, and one is without. And the big thing about without is that there must be some amount of friction, or else it'll slide and it'll act basically like a box or like any other object sliding down an inclined plane, right? However, friction does not do work because this is not kinetic friction, but instead static friction. remember that energy is going to be conserved even when rolling without sliding or slipping. All right. Now let's move on to our work. All right. So, first question: ball of mass m and radius r has a moment of inertia of 2 over 5 mr squared. Ball is released from rest and rolls down this ramp with no frictional loss of energy, then projected vertically upward off the ramp, shown in the diagram, reaching a maximum height of y max. Determine the maximum height in terms of range. All right. So let's start doing this problem. And if you're in Physics C and you just did the roller coaster project, this will seem very familiar, but I'm going to go through the entire process. So this is going to be a conservation of energy problem, right? So we have this ramp, we have a ball from here, we have a total change in height of h, and at this bottom point there is some amount of kinetic energy, right? At this point there's some amount of potential energy, and once this is released, this turns into a kinematics problem, where we need to determine the maximum height given some sort of velocity, right? So let's first write out our conservation of energy equations, right? So we have our initial potential energy plus our initial kinetic energy is going to be equal to our final potential energy plus our final kinetic energy. And this little dip here, this doesn't really matter because the only change in height is h, right? We don't need to count like here and then do another equation. The big thing is that there's a total height difference of h. So we can say that there is no potential energy at this point, and we can say that there is no kinetic energy at this point because it's released from rest. So that means that our mgh is going to be equal to our total kinetic energy, which I stated before was 1 over 2 mv squared plus 1 over 2 I omega squared, right? So we know that our moment of inertia is going to be equal to 2 over 5, right? Yeah, it's a sphere. So 2 over 5 mr squared, right? So at this point, we also know that our omega, our angular speed, is equal to v over r, right? This is a basic rotational analog. So let's start doing this problem. So that means that mgh is equal to 1 over 2 mv squared plus 1 over 2 times 2 over 5 mr squared times v squared over r squared, right? Because this is omega squared, which is v over r squared, right? So we can say this, and I'm just going to, I'm going to do this. Let's move this over here, make this just a bit smaller so I have more room to work with, right? Okay, so moving on from here, we now know that our mgh is equal to 1 over 2 mv squared plus these can cancel out, these cancel out, so this is 1 over 5 mv squared. And the reason why I said this was very almost nostalgic for a lot of the Physics C people was because this equation was basically used way too much. It was overused, and the only change was that we also had this. But that's not important for now. So we can keep on doing this problem. These combined together, this means that this is mgh equals 7 over 10 mv squared. So now if we cancel off some stuff and move some stuff around, we know that our v squared is equal to 10gh over 7, right? And we don't even need to take the square root of this later because now we get into our kinematic part. Our maximum height is going to be equal to v squared over 2g. And if you want to do the math, you can. But this is the equation that I'm going to show you for now. And this is why, if you still remember from, I'm pretty sure the first lesson, I talked about how for projectile motion, we have v squared sine squared theta over 2g for our maximum height. And I won't get into that for now. If you want to look at that old video, that's fine. But this is the big thing, v squared over 2g. And so we can just quite literally just plug this straight in, which equals to 10gh over 2 times 7 is 14g. We cancel off the g, and now we can determine that our maximum y, our maximum height in terms of h, is going to be 5 over 7h. And if we look back at our slideshow, we can see that right here with option D. All right. So on to the next problem. And remember that these are very difficult. If you're stuck on one of these, I would strongly recommend you just probably skip them or look at them much later, right? So this one is quite unique. The moment of inertia of a uniform equilateral triangle with mass m about side length a, about an axis through one of its sides and parallel to that side, is 1 over 8 ma squared. That was quite a mouthful. What is the moment of inertia of a uniform irregular hexagon with mass m and a side length a about an axis through two opposite vertices? Right, so this is some questionable wording, but basically it's saying, given that a triangle, given the moment of inertia of a triangle with a mass of m and a side length of a, with the moment of inertia passing through this axis, right? And that moment of inertia being 1 over 8 ma squared, find the moment of inertia of a regular hexagon with a mass of m, let's just say that, side length of a, and going through with a moment of inertia around an axis like this. So if you're cheeky, search it up, you get the answer, but that's not going to help you. So let's start going through this, right? So let's split this hexagon into 6 parts, right? Because this hexagon is just 6 of these equilateral triangles, right? I'm wonderful at drawing, if you couldn't tell. This is why I shouldn't teach. Anyways, we have 4 triangles that are already going to be doing basically this, right? They all already have this moment of inertia. If we look at this triangle, this triangle, this triangle, and this triangle, we can see that the moment of inertia given basically satisfies this, right? This triangle is going to be spinning on one of these sides. This triangle is going to be spinning on one of these sides. Same goes for this and this, right? So for those ones, we can say that we have 4 triangles that are going by this with a mass of the big M over 6, right? So that's going to be 4 times 1 over 8 times 1 over 6m times a squared, right? And so these are going to be these triangles, and I can even draw these in a different color, right? So these triangles. I'm sorry for like blinding you guys with this red, but I'm too lazy to do color differences, right? Now we have 2 more triangles, right? We have 2 interesting triangles, this one and this one. And these, they don't spin on one of the axes, right? They spin, if we were to draw this out, they spin on this axis, right? And so now is where we bring in the parallel axis theorem that I was talking about before, right? So we have our parallel axis is equal to our center of mass plus md squared. And a mistake that I made while I was originally solving these problems was, oh yeah, I have the original, I'm already given this moment of inertia, so that means that I can just go from here, plug that into here, and then just do, and since this height is going to be square root of 3 over 2 times a, and I'll show you how to do that later. I just said, oh yeah, so that means that this is 1 over 8 ma squared plus m times 3 over 4, right? So 3 over 4 ma squared or something like that. Like, oh yeah, that's going to be the parallel axis theorem. And that's going to be my moment of inertia. Wrong, I'm an idiot. So how this actually works, let's first address how I got square root of 3 over 2. Remember that this is an equilateral triangle, and how equilateral triangles work, we have technically 2 triangles, 2 30, 60, 90 triangles with a side ratio of 1 square root of 3, 2. And given that this 2 is going to be a, that means that this is a over 2, and that this is square root of 3 over 2a, right? And so that's how we can determine this length. But the critical error that I made in that assessment was that I forgot that this is not the center of mass, right? This is not the center of mass. This is not the moment of inertia of the center of mass. And remember that if it is not the center of mass, this won't work. So the really interesting thing is now we got to do some geometry, something that I'm really bad at. So if you remember anything from geometry, which I don't, there's something known as the centroid, right? And the unique thing about the centroid is, I can't draw, but the entire thing is, the centroid is a point where these basically the centers of these meet, and this is going to be the center of mass of the triangle. And the very unique thing about this is that all of these are split like are split in a 2-to-1 kind of ratio, where this is going to be 2 out of 3 of this side length, and this is going to be 1 over 3 of this side length, right? And so now we know about this. Let's say that this is a centroid, and now we have a little game plan, right? So we're given the moment of inertia of this about this axis, right? So we first need to find the moment of inertia for the center of mass, right? So we're going to need to find that given this and this, and from there we can take it up to here with the center of mass moment of inertia. We can find the moment of inertia around this axis, right? So let's do just that. We're given that our moment of inertia around this axis is 1 over 8 times ma squared, right? And so given that our equation, I'm going to write this here in a different color. We have this equation, right? So, given that equation, we know this, and we know this, right? We know that this entire side length is going to be square root of 3 over 2a. We know that from the centroid to this shorter edge, this is going to be the square root of 3 over 6a. And we know that from here, this is going to be the square root of 3 over 3a, right? And that's just because, remember that the centroid is going to divide this side in a 2-to-1 ratio. And so we get that our moment of inertia of our center of mass plus, what is that, 3 over 36, which is going to be 1 over 12a squared times m, is going to give us this. And the reason why I can say that is because square root of 3 over 6 squared is going to give you 3 over 36, which is 1 over 12, right? So that means that our center of mass moment of inertia is going to be 1 over 8 minus 1 over 12 times ma squared, right? Oh, shoot, I did this wrong. And given that, we know that this is going to be 3 over 24 minus 2 over 24, which is going to give us 1 over 24, right? And so that means that the moment of inertia about the center of mass is going to be, and I can just write this here, it's going to be 1 over 24 ma squared. And so that's the first step. Second step is to determine the moment of inertia about that axis, right? So now we can plug it into this equation once again. Our axis moment of inertia is going to be 1 over 24 ma squared plus, what is that distance? Square root of 3 over 3, right? And that's going to give us 3 over 9, right? So 1 over 3 ma squared, right? And so if we were to write this out, that means that this would be 8 over 24 plus 9 over 24, which is going to give us, 1 over 24 plus 8 over 24 is 9 over 24, and 9 over 24, we can simplify that into 3 over 8 ma squared. All right, we're pretty much done here. We just need to add that to this part. So we have 2 of these rectangles, not rectangles, 2 of these triangles, each with a mass of m over 6, remember? And so we have this from the red, right? And so we can add on 2 times 3 over 8 times 1 over 6m times a squared, right? And so if we write this all out, that means that we, if we just, it's going to be 4 over 48, right? So that's 1 over 12, 1 over 12. Let me just move this all aside for a moment. Let's do that. Make this smaller, right? So that means, let's move this over here. That means that we have 4 over 48, which is going to be 1 over 12 ma squared plus, and hopefully I'm doing this wrong, right, this is the first time I'm doing this. That's going to be 6 over 48, which is, that's going to give us an answer of 5/24 ma squared. And if we look back, and I'm just going to double check this for a moment because that's the first time I've done this. So excuse me for just one moment. Sorry about the inconvenience. I'm just double checking myself here. See if I got it right. All right, and so if we look back at the correct screen, let's go here. We're going to see that that's going to give us option B, which is going to be 5/24 ma squared, right? Yeah, these are going to be really hard. I'm sorry. This is just a really hard unit. But we're on to the next problem now. So looking at this, let me just clear that out. So two pulleys are made with the same metal with density rho. That probably doesn't matter. Pulley A is a uniform disc with radius r. Pulley B is identical except for a circle of r/2 removed from the center, and I'm assuming that's with a radius of r/2. When two boxes are connected over the pulleys through a massless rope and move without slipping, what is the ratio between the accelerations in system A and B? The mass of pulley A is big M plus little m, right? Okay, so usually I would probably go, oh, Atwood machine, ha 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 ha. Problem is that doesn't work. Since they move without slipping, that means that the pulley also does something, and we need that, and it also has a mass, right? So let's start working on this, right? So we have two pulleys with a mass of m, a mass of little m, and a pulley with a mass of m plus big M, right? So there's a few equations that we need to determine first, right? Since this side is pulling down and this side is pulling up, we need to determine the tension forces of each. So I'm going to label this T big M and T little m, right? This is going to be indistinguishable. So that means that our mg, our ma, right, for our big mass, is going to be, so this is net force, right? Net force is going to be equal to our gravity minus our tension, right? So that means that our mass times acceleration is equal to our mass times gravity minus our tension force, right? And this is for big M. For little m, we have our acceleration is going to be our tension force minus our gravity, since we know that it's going to be going in this direction, right? With gravity pulling down. So now that we have these two equations, we have our final equation, which is that our force times our radius is going to be equal, so this is going to be the torque is equal to moment of inertia times angular acceleration equation that I was talking about earlier, right? And so that's going to give us Fr is equal to I alpha. And our force is going to be the tensions, right? So that's going to be tension for big minus tension for small is equal to this times R, right? And so let's start combining these equations together. So we know that from this equation that our tension for our big M is going to be mg minus ma, right? If we just move this here and move this here and move this here, that's what we get. And for little m, our tension force is going to be mg plus ma, right? And these are small, these are big. And so if we combine these all together, I'm just going to get these out of the way. That means that our tension force is going to be equal to mg minus big Ma minus little mg minus little ma, right? Because we have a minus sign here and we just plug it in. Times r is equal to our moment of inertia times our acceleration divided by r, right? And so what we're doing here is we're finding a general expression for our acceleration for later, right? So let's first move this, just make this slightly smaller, right, around that size. And now we can start simplifying this, right? Let's first move our r to the other side. Fireworks, I miss those. So I times our acceleration divided by r squared. And we can start rearranging these, right? So this is going to be m, big mg, minus little mg, minus big ma, minus little ma, right? And so this is going to be equal to m minus m, big M minus little mg, minus big M plus big little ma, right? So we can move this, let's write this out here again, because we're going to be moving this equation over here, and that's going to give us ia over r squared plus m plus ma is equal to m minus mg, right? So we can factor out the a. We can say that this is a times I over r squared plus big M plus little m equals big M minus little mg, right? Now we can move this over this entire thing over to this side by just dividing by this entire block. And just let me move this, please. Oh no, it's cutting it off already. Please work with me. Thank you. How do I do this? I move that here. Right. Okay. So next up, let's first clear that. Now that we've moved it to this side, now we have a general equation for our acceleration, which is going to be big M minus little mg divided by I over r squared plus a big M plus little m. And this is really intimidating, because it is, but we're going to be getting through it very soon, right? So now that we have these, let's, the big thing that's going to change is going to be our moment of inertia, right? So in our final equation, we're going to have the acceleration for probably our pulley B divided by our acceleration over our pulley A. And so these elements are going to be repeated. These elements are going to, this entire portion is going to be repeated. The only difference is going to be here, right? The only difference is actually just going to be our moment of inertia. This element is going to stay the same. These elements are going to stay the same. This is just going to change it to a 1. So now we have basically 1 divided by 1 over our b divided by 1 over, 1 over our ib plus 1 divided by 1 over our ia plus 1. And if you want to double check this, you can. It's not really that hard. You can just see that basically these elements are just going to repeat, and if I just plug them in, they can cancel off. And so if we were to rearrange this, this is going to give us ia plus 1, I believe. Divided by IB plus 1. Actually, let me see. This is IA over IB. Okay, sorry, I did that entire portion wrong. It's going to be the ratio between our IA, not IA, our pulley A over pulley B. So this is going to be 1 over I A plus 1 over I B plus 1. And I just gave an explanation of how these can simplify. Remember that this turns into 1. This basically gets canceled off. And so this equals IB plus 1 over IA plus 1. And so that's going to be our equation for later. And our big thing now is to just find our moment of inertia. And this technically doesn't completely work. Actually, no, it does. But what I'm trying to get at is our moment of inertia for both of these is going to be some constant times our mass, which is big M plus little m, r squared. So technically, we only need this kind of constant thing, right? Because this is going to be canceled off as well. So let's go back here, and we can just say that this is going to be our constant for b plus 1 over our constant of a plus 1, right? And so let's go back and actually find these constants, right? So for our pulley A, this is pretty simple. We just have a little pulley here with these, right? And so our pulley, I'm pretty sure it's said to be a disk. So this is just going to be for our moment of inertia of A, that's just going to be 1 over 2 times big M plus little m r squared, right? So our constant for A is going to be 1 over 2, right? This is big. On the other hand, let's first select this and move this a little bit away from, no, I don't want to rotate this. Please, let me do something. Please. Work with me. There we go. So, this is one big component, right? This is all for, please work. Oh my god. Sorry. This is for pulley A, right? This is pulley A. Pulley A. And I know this video is going to be really long. I'm very sorry. Now for pulley B, we have a cut in this, right? We have a circle cut out with a radius of r over 2, right? So we can say that our moment of inertia for IB is going to be 1 over 2 m plus m little m r squared. That's all the same. Minus this little chunk in here, right? So that's going to be 1 over 2. Oh, I should probably move this over a bit. So we have IB is equal to 1 over 2 big M plus little m r squared minus 1 over 2 times the mass of this little thing is going to be this entire portion divided by 4, right? That's how area works, or like at least how this problem is supposed to work. And so times m plus little m over 4 times the radius is r over 2, so that's going to be multiplied by another 1 over 4 r squared, right? And so if we combine this all together, this is basically saying 1 over 2 m plus, like this entire chunk. It's going to, okay, so this is going to be m plus m r squared times, this is 1 over 2 minus, what is this, 1 over 2 times 1 over 16, which is 1 over 32. And this is going to give us 15 over 32 of big M plus little m r squared, right? So that means that our constant is going to be 15 over 32, right? So this, that is the wrong button. But if I were to select this successfully, which I did not, but I don't care enough right now. Sorry. Ooh. Ooh. I need sleep. I miss sleep. Anyways, this is for pulley B, right? Pulley B. So we have our constants here. We can just plug these in. So this means that our ratio is going to be 15 over 32 plus 1 divided by 1 over 2 plus 1. And if we were to simplify this, which I'm too tired to do so right now, we will get 47 over 48. And finally, if we look back, we see that we get option A, which is going to be 47 over 48. All right, let's continue. So, what is this? As shown in the figure, a ping pong ball. Okay, I'm too lazy to read that entire thing. So, I'm gonna read the entire thing anyways. Just give me one moment. Okay, so as shown in the figure, ping pong ball with mass m, initial horizontal velocity v, angular velocity omega, contact with the ground. Friction is not negligible, so both angular velocity and regular velocity changes. What is the critical velocity such that the ping pong will stop and remain stopped? Treat the ping pong ball like a hollow sphere. So you might think, oh, it's 0. It's not 0, sadly. So the big thing here is we need to kind of determine the equation. So the big thing is, oh no, don't remove that. Big thing is we have some amount of momentum and some amount of angular momentum, right? So our P equals mv, and we also have our angular momentum, which is also denoted as PR, is equal to our I omega, right? So when it's changing the derivatives of these, remember that our impulse is going to be the derivative, so we can say that as a function of time, we have ft equals m delta v, right? Because our velocity is changing due to friction, and for this, we have frt, right? Because it's our impulse times radius, is going to be equal to our moment of inertia, and we see that this is a hollow sphere. It says to treat the ping pong ball as a hollow sphere, so that means that our moment of inertia is going to be 2 over 3 mr squared times, well, not change, change in our angular velocity, right? So there's a critical point in time where both of these must be equal, and so we can denote this as, we can divide this, we can say that, divide both sides by r. Now we get ft is equal to 2 over 3 mr delta omega, right? And now we can set these two equations equivalent to each other. So we have m delta v is equal to 2 over 3 mr delta w, right? That means if we cross this out, our critical velocity is going to be equal to 2 over 3 r omega. And if we look back, finally, once again, back here, we see that that's going to give us option A. And like a little cheat code here is, it's probably not going to be something really confusing. So just probably take the moment of inertia. It's probably going to be something really similar to that. So next, we have a two-parter problem. A 3-meter long massless rod is free to rotate horizontally about its center. Two 5-kilogram point masses are originally located at the ends of the rod, free to slide on the frictionless rod, and are kept from flying off the rod by an inflexible massless rope that connects the two objects. Originally, the system is rotating about 4 radians per second, so that's our angular speed. Assume the system is completely frictionless and ignore any concerns about instability. Calculate the original tension of the rope. So this is the art of F equals ma problems. They have this really complicated, especially for angular momentum and like circular motion stuff. It's going to give you this really weird, really confusing kind of a lead up. It's like 3-meter long massless rod, rotate about its center. A bunch of point masses are located at the ends of the rod, free to slide on the frictionless rod for some reason, kept from flying off from an inflexible massless rod. Wow, such big words. And you see this a lot. There's some weird stuff like, oh, on this tabletop, a piece of mud is dropped on a disc spinning at an omega or something like that. But if we just write out this problem and simplify it, as said before with the F equals ma tactics from I think day 2, we can kind of simplify this problem and make this a lot easier for us. So calculate the original tension in the rope, right? If we think about this, this is really easy. We just have 2 point masses hooked together by a rope. Remember that the diameter is going to be 3 meters. Each of these point masses is going to be 5 kilograms. And so that means we need to find the tension of the rope, right? So this kind of motion. So the entire point is that the tension in the rope is going to be our centripetal force, which is going to be mv squared over r, or conversely, our rotational analog is going to give us m omega squared r, right? Sorry. Remember that this is our diameter, right? So that means that our radius is going to be 1.5 meters. I just realized if my handwriting looks really bad, just comment. Just let me know. I'll try my best to improve it. I'm kind of just speedrunning right now. But we have our radius now. We know that our angular speed, our angular velocity originally is going to be 4 radians per second, right? So that means our mass is 5 kilograms. So our tension force must equal our centripetal force, which means that our tangent force equals 5 times 16 times 1.5. And if we plug that in, that's 80 times 1.5, which is going to give us 120 newtons. And if we look back at our thing, we can see that that option is going to give us option C. All right, next, the rope is slowly tightened by a small massless rope. Rope is tightened by a rope. By a small massless motor attached to one of the objects. It is done in such a way to pull the two objects closer to the center of the rotating rod. How much work is done by the motor by pulling the two objects from the ends of the rod until they are each 0.5 meters from the center of rotation? Okay, more complicated lingo. It's not really complicated. So we now have a motor in the middle of this, right? We have a big boy motor that's pulling these two in. And I kid you not, this is the original diagram that I drew. So we know that these are originally 1.5 meters away from each other, right? Like the radius is 1.5 meters from the center, right? This motor pulls these two objects in until they're only 0.5 meters away. And I remember seeing a really elegant solution to this, but I'm too dumb to comprehend it, so we're just going to stick with my stupid intuition, right? So we know that work is our change in energy, right? And what better way of saying this by using the equations that we learned today, which is rotational kinetic energy, right? We know that there is not really much like translational rotational energy here, translational kinetic energy. So we're only going to be calculating rotational energy, right? So here's where the conservation of angular momentum comes in. We have our original I omega is equal to our final I omega, right? So that means what if our moment of inertia gets smaller, our angular speed is going to get larger, right? So our original, we know that our moment of inertia is going to be mr squared, right? This is for point masses, and so if the radius that means our radius or our moment of inertia is directly proportional to our radius squared, right? So if I don't think that's what I'm trying to say. I think it is. So that means that our radius, if our radius were to go down, it goes from 1.5 meters down to 0.5 meters, right? So radius is now 1 over 3. So radius prime is equal to 1 over 3 of the original r. That means that our moment of inertia, our changed moment of inertia, is going to be 1 over 9 of the original moment of inertia, right? Because it's going to be 1 over 3 squared, which is 1 over 9. The big thing that we need to take away from this is due to conservation of angular momentum, that means that our angular velocity, our final angular velocity, has to be 9 times our original angular velocity, right? Because our changed moment of inertia is 1 over 9 of the original one, so this needs to multiply by 9, right? So 1 over 9 times 9 is 1, times these, and that gives us our original. So now comes our energy, right? Rotational kinetic energy, remember that our equation is 1 over 2 I omega squared, which means that the final kinetic energy is going to be our final kinetic energy is going to be equal to 9 times our kinetic rotational our original rotational kinetic energy, right? Because this balances out, but since now it's squared, that means that we're basically multiplying by 9 omega again, right? So now we just need to find our original kinetic energy. So our original kinetic energy for one of these point masses is going to be 1 over 2 times mr squared times omega squared, right? And so that's going to give us 1 over 2 times 5 times, I believe, 2.25, right? 1.5 squared times, 4 squared? That's going to give us, I believe, 90 something, right? I forgot units. So that's our kinetic energy, right? Our original kinetic energy. We know that our final kinetic energy is going to be 9 times 90. So our final kinetic energy is going to be 810. And remember that our work is going to be our change in energy, right? So that means that our work is going to be equal to our final kinetic energy minus our initial kinetic energy. And we can already determine that that's 9 minus 1, which is 8. 8 times our initial kinetic energy. And that's going to give us 720 joules, right? I forgot units. So that means that our work is 720 for one of these masses. However, we have 2. So now our final work is going to be 720 times 2, which is 1,440 joules, right? And if we look, oh no, this is cut off. But if we look back, we can see that that's going to give us option D of 1,440 joules. Okay. Oh, sorry. Next, a disk of, and this was on the original worksheet from last week. So some of the poor kids who had to deal with it, I'm so sorry. This was actually for this unit. But basic kind of introduction. A disk of moment of inertia I, mass m, and radius r has a cord wrapped around tightly, shown in the diagram. Constant force of T is applied and accelerates the disk along a frictionless surface. Determine the ratio of translational kinetic energy to total kinetic energy of the disk. And from here, you can kind of do a little guess and check, right? The big thing is we know that our total kinetic energy, right? We know that there's going to be translational and rotational. It's going to be 1 over 2 mv squared plus 1 over 2 I omega squared. We can see that they keep I, they never change it. They never say 1 over 2 mr squared or something like that. So that's our total. We know that our translational energy is going to be 1 over 2 mv squared, right? So if we just look back at our answer choices, we can already eliminate A, B, and C, right? Because we have an addition sign here to implicate that it's both translational and rotational. So there's definitely some kind of plus on the bottom and something that's matching one of the top ones on the top. And so we can see that there are only 2 options that match that. So it's going to be D and E because all the rest of them have a plus. And so this matches this matches this. And from here, you could probably use intuition to guess, but I'm just going to do a full proof just because we need to learn. And I need to learn because I forgot the proof of this. So, translational energy, we have 1 over 2 mv squared, right? And, I remember how to do this. So, this is going to be equal to 1 over 2 m times a over t, right? Because that's how it works. A over t, or is it the other way around? I think it might be at. Oh, it's at, whoopsies. It's at squared, that's how math works. And so this means that this is 1 over 2 times m, and we know that from the the name, haha, roll credits, that this is going to be ft over m, right? Because a equals f divided by m squared. And so we can simplify this to say that this is 1 over 2 times, this is m divided by m squared. So we can say that this is ft squared, f squared t squared over 2m. And I know that the actual problem says that the constant force is called T, but that's just confusing. You're going to think it's tension or like a weird version of time, and so I'm going to keep it this way. Next, we have our rotational energy, right? Rotational energy is going to be 1 over 2 I omega squared. And we can basically use the same technique, where we have 1 over 2 times I times our angular acceleration times t squared, which is equal to 1 over 2 times I times, remember we have torque equals I alpha. So now we can say that this is our torque. Oh yeah, and also torque is equal to our force times our radius. So we can say that this is going to be F R T over I, right? Squared. So this is going to, in turn, I'm going to move this just a little bit so it's easier to see. Right? So this is going to give us 1 over 2. Remember that whole cross out thing. So we're going to get F squared R squared T squared over I, or 2I. Right? Let's see if this is all right. I'm pretty sure this is all right. All right, Let's select all this and move it to the side. Oh, God damn it. This is why you do your work early, kids. Anyways, now we're given, now we know our translational kinetic energy and our rotational kinetic energy, right? So, our task is to find the ratio between our translational and the total, right? Our total is going to be these two added together. So if we combine all of these, that means that we have f squared t squared over 2m divided by, what is that, f squared t squared over 2m plus f squared r squared t squared over 2I. Now we can do some crossing out. This crosses out, this crosses out, this crosses out. These, this, and this cross out. And so finally, we're given the ratio, which is 1 over m divided by 1 over m plus r squared over I. And at this point, you can probably determine, oh yeah, this has an r squared, this does not have an r squared, so it's probably going to be option D. But we're just going to solve this through. So now we can multiply by, I think it's im over im, right? This is the equivalent of multiplying by 1, but we can simplify some stuff, right? So we can say this cancels out, this cancels out with this cancels out with that. And so we can now say that this is I divided by I plus mr squared. And if we look back at our homie work, we can see that that's going to give us option D, which is I over mr squared plus I. Right? We're almost done. Only 2 more questions. I made a really long review, and I very much regret it. But I think it's going to be useful. Apparently my layer is broken. Let's just add a new paint layer. Alright. So, objects starting from rest can roll without slipping down an incline. So, roll without slipping. That's the last slide of our slideshow. Which of the following objects, each with mass m and radius r, but have the largest acceleration down the incline? And it gives us a few options. So, there's a really interesting equation, and I'm actually going to use it this time, which is going to be like this, right? Let's say we have an incline, right? And we have this object here, and it's rolling down. It's pulled by mg sine theta. It's got a little bit of friction that allows it to roll, right? Roll without slipping. And so our final acceleration is going to be based on both our this force and also our torque, right? From our friction. So we know that our torque is going to be equal to our I times alpha, and that is going to be equal to our frictional force times our radius is equal to our I alpha, right? So there's a really interesting way of doing this, which is we don't even need to write it like that. So this is f cosine theta, I think, right? Oh yeah, okay, I remember how to do this. So our force, it's not our frictional force, it's going to be mg sine theta r, right? That's our force times our radius, is going to be equal to our moment of inertia times alpha, right? And so the thing about a moment of inertia, this isn't from our center of mass. This object isn't going to be spinning in place. So that means that we need to apply parallel axis theorem, because it's going to be its point of contact is going to be here, and that means that its axis is also here, right? So that means that we need to apply parallel axis theorem, which means that our moment of inertia is going to be equal to our original moment of inertia. And remember how we talked about constants? That means that this is c mr squared plus the distance between these two, which is going to be another mr squared. So that's going to be equal to mr squared times 1 plus c. And this is pretty genius. This means that we can say, shoot, I shouldn't erase that. We can say this, right? And so if we add more, if we were to expand this, that means that this is mr squared times 1 plus c times our acceleration divided by our radius, right? That's a rotational analog. We can cancel all of these off, right? We divide this on this side to make this 1 over r squared, and then multiply by r squared, and that's 1. We can also cancel off these m's, And now we get, now to find our acceleration, we can just divide 1 plus c from this side to here. So we can say that our acceleration is going to be equal to g sine of theta over 1 plus c. This is quite genius. This shows that given that our incline stays the same, and we don't change planets in the middle of testing, the only factor that's going to affect our acceleration is going to be this constant from our moment of inertia. This also means that the larger this constant will be, the smaller the acceleration will be, right? Because if we think about it, we can technically even say that a is going to be directly proportional to c, directly proportional to 1 over c, right? Because as c increases, a is going to decrease, right? And so that means that the object with the largest acceleration down the incline is going to be the object that has the smallest moment of inertia, right? And if we look back, we can see solid sphere, moment of inertia is 2 over 5 mr squared. Solid disk, I'm pretty sure that's 1 over 2 mr squared. Hollow spherical shell, that's 2 over 3. A hoop is going to be either, it's going to be mr squared, which means that the constants are going to be, by these orders, it's going to be 2 over 3, not 2 over 3, 2 over 5, 1 over 2, 2 over 3, and 1. The smallest c is going to be a, and so that's going to be our answer, which is a uniform solid sphere. Next, which of the following 4 objects, each with a uniform solid sphere from rest, would have the largest speed after the center of mass has moved through a vertical distance h? Now you might think, oh, time to pull in a conservation of energy. Actually, no. We already have the equation that I just showed. And that shows that mass and radius don't really matter. It's only the constant of the moment of inertia. And the thing is, all of these have the same moment of inertia. They're all spheres. Which means that our answer isn't going to be like B or something. The answer is actually E. All objects would have the same speed simply because they all have the same constant for a moment of inertia. And so that's going to end the lecture here. Thank you so much for staying with me. Sorry this took so long. I'm also sorry that this was posted so late. But I guess that's pretty much it. I'll see you guys, I'm pretty sure in a few days. And then we're going to talk about gravitation and work out the future of the club. So thank you so much for watching. Have a great day and enjoy learning physics.